So we've spent a bit of time defining these various states that we're calling orbitals that an electron can be in. An electron can be energetically excited into really any one of these states, or it can be relaxed right down to its ground state. And we have a lot of options, therefore we have a lot of different excitations, a lot of different emissions, and that gives us the complexity and the various barcodes that we've seen up to this point. What our goal is in this part of the lecture is to learn a little bit more of what the physical reality of these different states or orbitals actually are. We mentioned in the last lecture that the Bohr model relied on this notion of an orbit, right, like the Earth going around the sun. And as we go to the Schrödinger model, which this diagram is schematically depicting, really we change our mindset into more of a three-dimensional space orbital model. So the question then remains, what do the orbitals look like for each of these energetic states? And that is what brings us to this diagram. This is a depiction of the models of all of these different orbitals, right? These are regions of space, if you will. And so if we start at the simplest case and have a look down here at the 1s state, which we've defined last lecture, we see that it is a relatively simple sphere and a relatively small sphere. This should all make sense, because if an electron is going to be in its happy place, if it's going to be the most stable it can possibly be, which is the ground state, then it would like to be very close to the nucleus. The nucleus is where the positive charge is, so my electron would want to be there. It would want to be very close to the nucleus. In other words, it would like to be in a small region of space wrapped around that nucleus. And so this orbital, this 1s orbital, is, I think, the most intuitive of the entire set. It makes a lot of sense. What it's really saying, what its physical meaning is that there is a spherical region of space around the nucleus that we are expecting to find our electron inside, right? We are not being so prescriptive as to say, here is exactly where our electron is. We are being more probabilistic, and we are saying, this is a sphere where we are most likely to find our electron inside. Okay, and that is the state defined as 1s. That is our 1s state and our 1s orbital. Now, as we go up, as this electron gets excited and it goes into higher energy orbitals, the nearest being the 2s, we get a couple of things to realize here. We get a larger sphere, right? So it's a larger sphere. And that makes sense. This is actually analogous to the Bohr model. The Bohr model talked about orbits, and you could be orbiting along a large radius, or you could be orbiting along a smaller radius. That is analogous to this 1s, 2s comparison. As you go up to the n equals 2 level, principal quantum number 2, and you're in the s state, you are still in a sphere. And no, that is not what the S stands for. It doesn't stand for sphere, but it is spherical in shape. And so the 2s orbital is what we would think of as a larger sphere. And then likewise, you can continue that pattern and have a look at the 3s orbital, a larger sphere still. And so we get one of the really fundamental take-home messages of today, which is that the principal quantum number n, among other things, obviously it's a significant determiner of energy, right? So if you're in a higher n value, you have more energy for sure. But it is also a really strong determining factor of size. So the n equals 3 orbital is most definitely bigger than the n equals 2 orbital, right? So a 2s is definitely a smaller region of space than a 3s. And again, this is analogous to the whole Bohr model. Now, it gets a little bit more bizarre, I would argue, as we go looking at these other L values, right? Our p orbitals and our d orbitals. First things first, these are all plotted for us along what's called a Cartesian coordinate system. So we've got our z, our x, and our y axes. And what that allows us to do is, first of all, we notice that if we're looking at these p orbitals, and remember there would be 3 of them, and they're grouped as a trio here. First of all, they've got these 2 lobes, and those lobes are oriented in various directions, okay? And that is the key differentiator between all three of these orbitals. One is oriented straight up and down, one is oriented along this axis, and then the other is oriented along that axis. They are effectively identical orbitals, differing only in the direction they point in three-dimensional space. And so this is interesting information because, you know, this we can draw several connections here. One is, I think now it should be clear why all three of the 2p orbitals are actually exactly the same energy. We have a word for that. We call it degenerate. So we would say that these 2p orbitals are degenerate orbitals. And it should be clear why. They're all identical. There is no difference between any of them. They just point in different directions. And so because they point in different directions, it is probably self-explanatory why we can give them labels X, Y, and Z. We can talk about the 2px orbital being oriented along the x-axis, likewise the 2py orbital being oriented along the y-axis, and then obviously the 2pz being oriented along the z-axis. So these are those different orbitals, and just to be clear, these are, just like the 1s, 2s, and 3s orbitals, describing a region of space where I expect to find an electron. So if I excite my electron to the 2px state, for example, then I expect it to be distributed like this image, which is odd, I think. And if you don't think it's odd, allow me to elaborate even just a little bit. This is, let's look at the 2pz actually. The 2pz is probably a little clearer for us to look at because it's oriented in an axis that we can look directly on its side. Let me zoom in here just for a second to show you what I'm talking about here. This particular diagram is essentially color-coded. It's coloring each of the lobes a different color so that they can be clearly distinguished. There's a reason for that, but we'll get to that later. There is what is called a node directly between these two colors. In other words, this map, if you will, this map of three-dimensional space where we're asking ourselves where are we likely to find this electron, actually has a surface of 0 probability separating each of these lobes. Okay, so you've got some likelihood of finding your electron up in this space. You've got an equal likelihood of potentially finding your electron down in this space. But you have a literal 0 chance of finding the electron in the interstitial space between those two lobes. So in that plane, that literal xy plane in this particular diagram that cuts those two lobes, defines a surface that the electron will not exist in, right? If these are probabilistic maps, what we're learning here is that the probability that cuts these two lobes is definitively 0, and that's a bizarre thing for a whole bunch of reasons, not the least of which is if the electron is likely to be up in this top part of the lobe, or it's likely to be down in this bottom part of the lobe, how does it get from the top to the bottom if it is literally not allowed to cross that interstitial region? These are bizarre questions that quantum mechanics has, in spades. There's all kinds of them. But I'll draw you to an analogy here that hopefully will reconcile this a little bit in your mind. You can take a skipping rope, for example, and you can take that skipping rope and create a wave in that skipping rope with a friend holding on to the other end. And as you add more energy to that, you would notice that you can actually create two lobes in that way. You can just swing the skipping rope so that goes up and then down and then up and down. But if you start swinging that much more vigorously, in other words, if you give it more energy, you'll notice that it can actually swing around with two lobes on it. And the middle part of that skipping rope would actually be stationary. It's actually cool to try. So if you try it, you'll see what I'm talking about. The middle part of that skipping rope is stationary. In other words, there's no energy, there's no wave, there's no nothing in your skipping rope right at the middle. Yet it's still possible for it to bounce up and down, right? And so that's sort of an odd thing, but this is a very similar scenario to what we've got right here. And a skipping rope can demonstrate and exhibit waves. This orbital picture is a wave-like picture, and this is really a fundamental tenet of quantum mechanics. It is that particles are described using the mathematics and the sort of mental imagery that we think of waves. And it's maybe a little bit odd, maybe a little bit bizarre, but it is experimentally verifiable. There's a key. So there is lots of evidence, if you will, and evidence is something that we always look for in science, of course. And so if I go up now and look at the 3p orbitals, you won't be surprised to notice that they look just like the 2p orbitals, except they're bigger. And then that leaves finally the 3D orbitals to talk about, which have more lobes. And this is a consistent trend. As you work your way up this diagram, you continue to add more and more lobes to these distributions. And so you get these clover leaf type shapes here defining the d orbitals, where you only had the 2 lobes here for the p orbitals. But that is a consistent pattern that would continue on up into the Fs, for example. That's just how this works. And so what these images up here on the top right are telling us is that if I have an electron that is described by a 3D XZ orbital, right? And again, these labels should probably make sense. This is an orbital spread along the XZ plane. Then I've got a likelihood to find it, in any one of these 4 quadrants. But just like my 2pz orbital had that nodal plane, right? A node is a region of space where these diagrams go to 0. They vanish. There is no likelihood of finding our electron there. So there is a node that cuts this p orbital in half. For the d's, there are 2 nodes, right? One that cuts between there and one that cuts between there. And so for every time you have more lobes, you have more nodes associated with it as well. And so you have this more, more stratified distribution of how the electron is spread out in space. Larger, of course, right? This is a larger spatial region than the others, but nonetheless, it is still segmented in the way that we might expect. All right, so what I'd like to do now is take a little bit of a deeper dive into what these orbitals actually are, what they're telling us. We think of them as a region of space where we're likely to find an electron, and so when our electron is in any one of these various states, we can, in our minds, imagine the distribution of that electron in space. What I'd like to do now is maybe take a quick look at some 3-dimensional models of these same orbitals, just to get a more complete picture rather than these static 2D models that we're looking at right now. All right, so what we're looking at here is a computer model of these same states. You'll notice that in my window here, I've got my n value specified and I've got my L value specified. So we're looking at a 1s orbital right now, which is really not all that interesting. It's just a sphere. But the important thing I think to glean from this image is that it is, a useful thing to think of these as clouds per se. In other words, the thickness of this cloud, or the brightness of what you're looking at on this model, corresponds roughly to the probability that you'll find an electron in that particular region of space. So although in the previous image you would have looked at a sphere, and it would have looked like a hard sphere, in reality this is really just a probability map, and that sphere sort of fades out as you go farther and farther away from the nucleus. And so the likelihood of us finding an electron way out here in this region here is pretty low, but pretty good in here closer to the nucleus. And that makes sense, of course, because that's where the electron wants to be. So in textbooks, we often We often depict these as hard spheres, and we say that there's an electron in there, but the better way to really think of that, and the more realistic thing here, is that this is really more of a cloud where our probability looks like a sphere, but it's smoothly changing off into space. So let's take a look at some others here. I can select the n equals 2 state, and again, the n equals 2 state is also a sphere. I'm spinning it around and it looks the same no matter how I look at it. But the n equals 2, the 2s, is interesting. It's got, what looks like sort of a layered structure to this. And so what I'm going to do is I'm going to slice this orbital right through the middle so that we can look at it, look at a slice. Okay, so the cloud has been sliced directly through, and look at what we're looking at here. So where this cloud is bright is, again, where I have that relatively high probability of finding my electron. And where it's dark is where I don't have a probability of finding my electron. So my 2s orbital, this spherical orbital, has another one of these nodes in it that we keep talking about. And it is true that as we go up from n equals 1 to n equals 2, we'll have a node. And as we go from n equals 2 to n equals 3, we'll have 2 nodes. And that behavior is conserved no matter what. But in this spherical s orbital, that node is also a sphere. It's a really interesting outcome here, where we say that we're likely potentially to find an electron relatively close to the nucleus. That makes sense. We're also likely to find it in this region out here. We're very unlikely to find it very far away from the nucleus. Again, that makes sense. But there's this radial zone here, this sort of inner sphere, where it is what you might call a no-fly zone for electrons. Electrons absolutely not allowed to be there. And that's a bit of a bizarre result, but it is the result. It's Schrodinger's result. When you predict the different states that can exist for an atom like hydrogen or anything else, you predict this 2s state, and you predict that it has a node in it. And that pattern, again, that we talked about earlier, is beautifully conserved. But this is what a 2s orbital looks like. Let's walk through some others. Now that we're at the n equals 2 level, we have an L equals 1, or p orbital, available to us. And there's that familiar shape that we saw from the image in the past. We've got a region, 2 regions separated by a node in the middle. You don't need to pay a lot of attention to the colors here. They're just sort of smoothly changing. If I ignore the slicing, I can now see the sort of 3-dimensional version of this as I pass it back and forth. And again, similar interpretation here. I'm likely to find my particle or my electron over here, likely to find it here, but not at all likely to find it in the middle, which I would expect. There should be a node in any n equals 2 orbital. And as I flick through the various versions, the 2px, 2py, 2pz, I see that they're exactly the same. They're just oriented, of course, on different axes. Okay, and I've got my coordinate system indicated up here just to keep me aware of how these things are oriented in space. All right, so finally, maybe let's take a look at the n equals 3 level. And there we go. We can see the 3p orbitals, which have that same notion of a node on, or a lobe on this side and a lobe on this side, and the node in the middle. But notice there's another radial node here, right? And that's because we're up at the n equals 3 level. So this still looks like a p orbital. It's got, the nucleus would be located right here in the middle, and we've got some probability over here and some probability over here. But these lobes are now separated by yet another node, as we would expect, because we've jumped up to the n equals 3 state. Okay, so again, these are Schrodinger's solutions for all these different states, and they go way beyond Bohr's simple orbit model, right? So let's take a look at D's now, because the L equals 2 or D options are now available now that we're at the n equals 3 level. And here is an interesting result. So this is what we would call the 3DZ squared. This one's a bit unique, so let's leave it off just for a moment and take a look at some of the others. There is that cloverleaf pattern that I talked about earlier. If we switch over, here we can see those cloverleaf patterns that we expected from the D's. And what we're looking at now is really just a 3-dimensional computer model of that. And so here are my cloverleaf pattern. I can see the 2 nodes very clearly splitting these lobes. And so I'm likely to find my electron really in any one of these quadrants, but not likely to find it in the middle. And of course I can flick through all the various versions of this, but really all it does is it turns this four-lobe pattern into various axes in space. And it's really only this special 3DZ squared one, which has more or less like a donut in the middle here with a lobe on either side. So it looks like a p orbital, but with a donut circling around through the middle. And so we can see that there is a nodal structure to this. So there is a node coming through here. There's a node coming through here as well. And so it obeys all of these rules about nodes that we know, but it does have a somewhat interesting shape. So with that will, I think, demonstrate what an orbital is, right? This is a probability map where the brightness on this map is regions of space that we're more likely to find our electrons in than others. And the darkness on this map is places where we're really not likely to find our electron at all. And to conceptualize these in sort of a static textbook-like drawing, that's where images like this come from. So you can see that they faithfully represent the orbitals that we were just looking at in the more realistic computer models, but it's important to understand the connection between the two. All right, so there you have it. What we did in this lecture is we reminded ourselves about the Bohr model, which was really just a series of fixed states in a relatively simple way. And then we expanded on that by incorporating some of Schrodinger's ideas, which were that there could be many, many states at every one of those different n levels. And we assigned a number to them. These are called quantum numbers. We had the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. And we discovered the pattern, the beautiful pattern in all of these different energy states. And we used Schrodinger's notion and Schrodinger's equation actually to help us envision what each of these different orbitals actually means. They're probability maps. They tell us where electrons are likely to be in space. So where Bohr had planetary orbits, Schrodinger has orbitals, three-dimensional regions of space. And we saw, again, yet even more patterns in the nodes that exist in these orbitals, which at this point in time is maybe just more of a fun fact. But as we move on in this course, we're going to discover reasons why those nodes and the structures of those orbitals actually helps us predict chemistry and actually helps us understand why some systems behave the way they do. It's an incredibly powerful tool. So now we know about orbitals, we know about all of the different energy states that an electron can occupy within an atom, and we understand the pattern so that we could extend that arbitrarily to any number of states. Our job now becomes to apply all of this pattern to the atoms that we know and love and try to think about what are the electrons in all of the elements of the periodic table doing and how are they distributed among these orbitals. So that's coming up next.